So today we are going to talk about the types of vectors. So the first one that we're going to talk about is null vectors. So if you know the meaning of null, you might have an idea of what this vector is about. You can null vector, or another name that you find for this vector is zero vector. So looking at the term zero, there might be some things running in your mind. So let's see what is the definition of this vector. So it is a vector. It is a vector having zero magnitude, having zero magnitude, and is denoted by and is denoted by is denoted by 0 with a vector arrow over it. So this is the actual um, definition and the denotation of a null vector. So what does zero magnitude actually mean? So we must talk about that. Think about it. If you have a vector, its magnitude is going to be represented by the line, and the head is going to give the direction. So in this case, we don't need to care about the direction, but we need to care about the magnitude. So if this length is shortened, suppose it's shortened, and it gets more short, then think about it. At a point, it's just going to be like a point. Even so, like, it does not have a magnitude. So that's what it means when it does not have a magnitude. So if it does not have a magnitude, how can you say what the direction is? Because if I had an arrow, I could have kept the arrowhead over here or over here. So there are two direction possibilities if I have a line. But if I have a point, so you can think of zero magnitude as a point, where would you keep the arrow? You can keep it over here or here or here. So the direction of arrow can be in any direction. So that's why we say that null vector has an arbitrary direction. So we can say it may take arbitrary direction. Okay. Also, where does this vector actually occur in? So we talked about that this has an arbitrary direction, this has zero magnitude, but if you think about it, there might be a very few cases where you think this vector might be useful. So let's talk why this vector arrives. So this vector comes up when we do subtraction. So it's a special case of a subtraction. So it is introduced it is introduced to give meaning meaning to operations like to give meaning to operations like so what kind of operations? As I said, it's going to be subtraction. So suppose I subtracted a vector a with another vector a, then that will leave me with nothing, but it does not leave me with nothing. Since subtracting two vectors leads a vector or gives a vector, you need to have the magnitude as 0, but it also must be a vector. So this is where zero vectors or null vectors actually comes up. So for example, so let's look at an example. So to make this much more clear, a body a body at rest. So if a body is at rest, it would have no velocity at all, which means the vector velocity will be a zero vector. Since if a body is at rest, suppose this man is at rest, the direction of its velocity cannot be found, so its direction is arbitrary. And since it's not moving, so it's at rest, it does not have a velocity, which means the magnitude will also be 0. So this is where null vectors or zero vectors actually come up in. So let's look at another one. The second type of vector that we are going to talk about is unit vector. So unit means one, which means that its magnitude might be 1. We are not sure. But let's look at the definition and check if we are right. So it is a vector. It is a vector having unit magnitude. So unit means 1. So let's write 1. So 1 unit magnitude. Okay. And so our guess was right. Since 0 vector meant the magnitude was 0, the unit vector means the magnitude is 1. So it is denoted by a letter with hat over it. So what does a hat represent? So this hat is a pretty unique word. Also this unit and this part also. Let's also make here 0 magnitude have 0 magnitude and arbitrary direction. Some important points. Okay, now let's look at what does the hat mean. So let's take an example and show what a unit vector is, which will make it much more clear what it is supposed to represent. So for example, suppose there was a unit vector called A. So we will represent it by A hat. So that's the hat. It kind of looks like a hat as well, like a roof of a house. So that's why it's called a hat. And the formula by you find this is a vector A. Suppose there is any random vector A and you divide it by the magnitude. Divided by the magnitude A. Okay, so this is the definition. So let's talk about why this is the definition. So let's take a look at a simple case and make sure why this is the definition. So let's look at a simple case. Suppose I had an acceleration. Suppose I had an acceleration which was 10 meter per second squared east. Let's just suppose that. And which means the magnitude of the acceleration is just 10. It's 10, right? The length is 10. And now, since we need to find this, so it's going to be 10 meter per second squared. We need to find a hat. From the definition, it must be a vector by the magnitude of vector A. So we have 10 meter per second east by 10 meter per second. That will give me 1 east. Okay, so we got 1 east. So look at this right over here. Do you think there is something missing? Yes, it's that there is no units. So which means the dimension of a hat or a unit vector is it's dimensionless, right? Because east only represents the direction and the units just cancelled out. And here the magnitude is still 1. So this is a very cool fact about unit vectors. So let's write something more right over here. Here the direction of a hat is along the direction of vector A, as you can see over here. Since our original acceleration was in the direction of east, our unit vector is also in the direction of east, right? Okay, so now let's see where do we actually use the unit vectors. So in Cartesian or Cartesian, so in Cartesian coordinate system, So coordinate system. The unit vectors, the unit vectors along x, y, and z or z axis are denoted by I cap, j cap, and k cap respectively. So in my notation, I don't keep the I don't keep the dot, but in books you might see the dot. It's just the way that I'm writing it. There is no hard or fast rule. So you can write the I with the dot and again keep the hat, but I don't like to keep it, so I'm not gonna keep it. Okay, so we wrote this. So let's see what is the Cartesian product. So Cartesian coordinate system. So suppose I have a coordinate system. So let's make a coordinate system. And I'm going to take it as a 3D coordinate system, which means I would have three different dimensions, I would say. So let's rotate this one, rotate this this way, and the one and another one that is coming out to the screen. So in actual, if this is the two axes, you wouldn't even actually see it. You would see that it comes out of the screen. But since I can't like actually make it go out of the screen, so think about it. Suppose I had these two lines, then from this point there will be a line that will come straight out. But since I can't do that, let's suppose it comes right over here. So actually this and this 90 degrees, this and this 90 degrees, this and this 90 degrees. So the angle between any two lines will be 90 degrees. Okay, so now let's label the coordinate systems. So you can actually label it by any way you like, but the way you do it, it's going to change the equations or the things that you're going to do. So it will change the formulas, but the concepts will remain the same. I'm going to use the x, y, and z coordinate systems in this fashion. You might see the y and z replaced or this flipped. So there are many other ways to writing it. I'll just represent x, y, and z. So if we have to talk about a unit vector in the x-axis, it will be I cap. And if we will have to talk about a unit vector in y-axis, it will be z cap. Similarly, if we have to talk about a unit vector in z-axis, it will be k cap. So now, where does this unit vectors come in usefulness? So we just talked about these axes. The unit vector along this axis will be represented by the following thing, but how does it help us? That's the thing we're going to talk about. So let's take an example. Let's take an example of force, since we are pretty chill and we pretty much know what is force. So force, suppose I have a 10 Newton force that is along x-axis. So I can just represent that it is along x-axis by using I cap. So this will mean that it is along x-axis. And the fact that this has no dimension, so it does not affect my unit. As well, it also has a magnitude of 1, which means it will not affect the number, right? Since you're just doing, so this is basically how this came up. It was 10 Newton, which is the magnitude, times the direction. So in units and dimension, okay, so let's add something more. You learn that there is a numeric value, there is a unit, and there is a direction. So in vectors, you will also have a direction, which means our numeric value was 10, our unit was Newton, and our dimension was 1 I cap. So this in turn gave us this. So not having a dimension, this being a dimensionless quantity, helps us. Okay, so let's write it in a much more formal way. So in a formal way, you would write 10 Newton force is acting along x-axis. X-axis. So that's the thing that this tells us. So 10 Newton of force is acting along x-axis. Okay, so this is why this is useful. This is useful because we can represent vectors and their directions in pretty short and simple ways, which everyone will understand. Instead of writing the force is acting along x-axis, we could just write vector F is equal to 10 newtons in the x-axis, which is I cap. Okay, now let's talk about another one. I think we are in the third one, which is parallel vectors. So let's go a little bit back. You can see this is dimensionless. So that's a very important fact, okay? So our unit vector is dimensionless. So I will also write this fact. This is dimensionless since you're dividing the units when you are doing division. Okay, so now let's talk about parallel vectors. I'm pretty sure you know what parallel is. So what do you think parallel means? Think about it. If so, two vectors or any amount of vectors that you want to take, but we are just going to take two for this case. Two vectors, A vector and B vector, or vector A or and vector B, are said to be parallel if the direction is parallel. Sounds about right, but what does this mean? So if they are parallel, they would have an angle between them. The angle between these two vectors will be 0 degrees, right? So if the direction is parallel, they are said to be parallel vectors. So the thing is, the direction must be parallel, or the theta must be 0 degrees. Okay, so let's take a look at some examples. Suppose I have a vector. So let's suppose this is our vector A. So this is 3 units of something if we are considering these boxes as units. And also, let me take another vector. This is another vector. Let's make it blue in color. Suppose this above vector is vector A and the vector below it is vector B. So right over here, the angle between them is 0 degrees and their directions, so this portion is also parallel. So this will be parallel vectors. Also, I can also do this. So I can rotate them if so. Let's rotate them, keep them right over here, and this will also be two parallel vectors since both the directions are in this direction. But what if I rotate one but I don't rotate the other? I think the arrow is kind of hard to see, so let's actually increase the size. Okay, so the arrowhead in same direction, but if the arrowheads are in different direction, would you still call them parallel vectors? I mean, you should, since the direction is still parallel, right? Since if you follow the direction, it's gonna go like this, and down here it's gonna go like this, but they are still parallel even though they are in opposite direction. Which means, suppose this is vector E, this is vector C. I'm not gonna write B, so it might be confusing. Oh, sorry. Let's write this as vector C and this as vector B. Or did I make it more confusing? Let's make it A dash then. Okay, A dash. A dash. The dash simplifies that it's something different. So right over here, if you have to measure the angle, would you say this is 0 degrees? Some might say this is 0 degrees, and in the definition we have only written 0 degrees, but actually it's 180 degrees. Okay, it's going to be 180 degrees. So when we are talking about right here, we only talked about this case, so we will have to write or 180 degrees. Okay, so now this, I think parallel vectors are pretty simple, so we have to talk about the next one. Okay, but before we go to the next one, I want to talk about a tiny little bit thing as well, because I kind of did not, I kind of stated that this must be equal. Like the magnitudes must not, can be equal or cannot be equal. So let's make this one unequal. So they can be unequal as well, since the direction is the only thing that must be parallel. It's not the magnitude that must be equal. If the magnitudes are equal and the directions are same, they will actually be called equal vectors that we will learn about pretty quickly. So let's move on to the next one. I think this is the fourth one, which is negative vectors. So what are negative vectors? So those vectors which have same magnitude and act on opposite direction which means the angle must be 180 degrees, right? So these are negative vectors. So theta must be 180 degrees. So if we have to opposite direction, so let's like dir. So if we have to represent this by an example, this is basically the example if the magnitude was equal. So let's move this right over here and make the magnitude equal. Let's line it up to make it much more easier for me. So this is negative vectors. Since a dash and b have same magnitude and act on opposite direction, they will be called negative vectors. And do you want to know why they are called negative vectors? Let's take a look at some examples. Suppose I have a vector which has 10, suppose no units, 10 I cap. Well, let's just give it some units. 10 meter per second. Let's say this is a velocity. 10 meter per second I cap. So if the negative vector of vector A will simply be minus A, isn't it? So it will be minus 10 meter per second I cap. So right over here, this B right over here is actually just negative A vector. That's why it's called negative vector, since you get the vector by adding a negative sign. So this is the vector and this is its negative vector. Okay, now let's talk about equal vectors. So what are equal vectors? So I talked about them a little bit earlier, but let's have a look at them right now. So those vectors which have same magnitude and same direction. Okay, which have same magnitude and same direction. So let's take a look at some examples. So let's go back to parallel vectors and copy this, since this is basically equal vectors. Vector A and this was vector B. So if you see, the magnitude is same as well as the direction is same, and I can actually take any vector, and if I'm not changing the direction, I can move it anywhere. So this is vector A wherever I move it. Even though I'm moving it very much, everywhere I'm moving it, unless I change the direction, it's gonna be vector A, which means I could actually move this vector like this, can't I? So, I'm moving it, moving it, moving it, and it overlaps. If it overlaps, it's actually called collinear vectors. Um, and co-terminal, co-initial, like there are many ways to represent. So this will be sufficing for many cases. So I can also do it like this. So this will be co-initial, or sorry, co-linear vectors, co-initial vectors, co-terminal. So there are many ways. We will talk about them later on. So I can actually overlap them, which means this vector B must also be equal to vector A. So this must be equal to vector A, which means they are the same vectors. They are basically the same vectors, just they are placed like this. So these are equal vectors. Now let's take a look at another one. So I think sixth. So the sixth one that we're gonna look at is collinear, collinear, collinear vectors. So what are collinear vectors? Co meaning same, linear meaning a line. So they must lie on the same line. So vectors that lie in the same line. So the key point will be the same line. They must lie on the same line. So let's just take two vectors. Um, let's take this vector right over here and let's keep it on this line. Yeah, um, that's good. And take another vector. Let's make it a little bit bigger so that they are not the same size. They can be the same size. I'm just making that they are not the same size. So this will be our vector A, this will be our vector B, and since they lie on the same line, which is this dotted line, if you can see right over here, which means they are collinear. So this line can also be equal to the first line, or it might not be. That's not our problem right now. It's just that they must be on the same line. So now the next one that we're gonna talk about is coplanar. So I think this is the seventh one, and we're gonna talk about coplanar. I'm not sure about the spellings, so be careful on that. Coplanar vectors. So co meaning same, planar meaning plane. So the vectors that lie in same plane. So vectors lying vectors lying on the same plane. So there are vectors lying on the same plane. Suppose I take a plane. So suppose this is a plane. Let's change the color so that it looks like a plane. So suppose this is a plane, and let's add some vectors. So this vector, the vector can be rotated in any ways. If they are in the same plane, it does. That's it. They just must be in the same plane. Okay. Let's change it to that. Let's add another arrow. Let's make it this one, and let's make it blue. Okay, not that blue, but this blue, and also make it bigger. Suppose this one is vector A, this one is vector B. So this vector A and vector B will be coplanar vectors. Of course, I can add more vectors. Like wherever there is vectors, you can generally add more vectors and you will get the same thing. And even if they are equal or something like that. Okay, so now these are coplanar vectors. So now I wanna ask you a question. How many vectors will always be coplanar? Coplanar. Think about it. How many vectors will always be coplanar? So since I asked you this question, you might think like 2 is obviously gonna be there. Since if I didn't ask you, then why would 2 not be there? Or you might think 3, 1. There might be multiple choices that you might think. But in truth, two vectors, two vectors are always, are always coplanar. We will also look at why this is the case. If this was a 3D drawing, then it would be much more easier, but I'll still try my best to represent why two vectors are always coplanar. So may or may not, may or may not, 3 or may not be coplanar. So think about it. If I have a vector, let's use shapes. Why shouldn't I use shapes? Suppose I take a vector, okay, this one, and I take another line. So right now I can't create a plane since this is only a line. And if I create another vector, so I can create a vector very close, very up, coming out of the screen, coming in the screen, going out the screen. So there are multiple ways I can do it. So in any way, suppose I do a plane. So let's actually make a coordinate system, which will, I think, make it much more easier. I'm not gonna label the coordinate system since it's not about labeling them right now. It's just about understanding how this actually works. Just think of them, they are mutually perpendicular. Since coordinates must be mutually perpendicular, so let's add any random vector. Suppose this is the vector, okay? So this is a vector that's floating in space. If I add any other vector, so let's make another vector. So let's take this vector, let's format it so that it's blue and it's like this, not that, like this. If I kept the vector like this, I can always make a plane that passes through this. So this time the plane might be like this. So a plane like this would pass through this, right? It would pretty easily pass through this. If I change this vector and so that I make it like this, a plane something like this would pass through it, right? And so on and so forth. Suppose I took like this, still a plane like this will pass through it. So you might have a question, why does always a plane pass through that point? And it's quite simple actually. Think about it. If I have this point, let's take it like this, and I rotated this point. If I kept them together and I rotated this from here to here, back here, and again go there, I can create a plane on any of the surfaces since I'm not limited. So this would be a plane. If I create it like this would be a plane, and so on and so forth. So let's just create some planes and to get an idea of what I'm talking about. So if this was the case, a plane like this would keep both the vectors, right? And if I move the plane, sorry, I move the vector like this, I can create a plane so that it's like this. Let's make another one that's bad. So from here to here to here. So if you look at any two vectors, so I'm taking a look at any vector. So let's also add another one. Let's create this one so that it's like maybe this. So let's create that. A plane like this would clearly be enough to hold the vectors, right? So now we need to talk about why, like why does this happen? So this occurs, not the greatest shape, but let's make do with it. This occurs since if we have one point, we can rotate it by any point and it will still create a plane. But look at any three of the vectors right over here. Do they always match up in the plane? Like in this case, none of them actually are in the same plane. This is in this plane, this is in that plane, and this is in this plane. Since this is a 2D figure, you might think, isn't all of them in the same plane? But it's not what I'm trying to show. Since this is a 2D page, it will look as if all of them are in the same plane, but they aren't, since I'm making a 3D figure. But think about it, which means two vectors will always be coplanar, but three vectors may or may not be coplanar. So that's a key insight that you must have in order to, I don't know why you must have it. I guess to understand vectors more, I would say. Okay, now let's talk about another one. I think it's 8. Yep, 8. So the eighth one is gonna be co-initial vectors. So co meaning same, initial meaning same point. So the vectors the vectors that have that have same origin. Same origin. This does not mean that it always has to be 0 comma 0, but it can be any point as per se, but they must start from the same point. Suppose this is our vector and we have another vector. Suppose this one. If they start from the same point, the vector can be in any orientation like this. If they start from the same point, it's gonna be co-initial vectors. Pretty simple as that. So let's also make this a little bit bigger. So here, our A vector and B vector are co-initial vector, and this point where they meet will be the origin. Yeah, I think that's pretty self-explanatory. So this is the origin, not 0 comma 0, but the origin where they meet. So origin, as to say where they came up from. Okay, so now the final one that we're going to talk about today. So this is the final one that is going to be discussed over here. There might be more types of vectors, little obscure one, that we have might not have discussed, but let's still ignore them and let's just talk about this one. The ninth one is position vector. So a vector which gives which gives which gives position of the body, which gives position of a body relative to an arbitrary origin, but this origin will actually be 0 comma 0. So this origin is going to be represented by 0 comma 0, whereas the other one might or might not be. So this one might or might not be 0 comma 0, but this will be represented by 0 comma 0, or generally. Okay, it's also not a hard and fast rule, but when we are talking about position vectors, it's generally 0 comma 0. It's very highly likely that it's 0 comma 0. So let's take some axis. Suppose this is one axis and another axis. So this will be axis, I think that's the pronunciation, or I'm not sure. um, so suppose there is a vector like this. We only kept two axis because I just want to explain the concept. It's not that I'm using it. And plus, my vector is lying on only two coordinates, which is, let's take this as x, this as y, and this will be origin, which means this point right over here will be 0 comma 0. So this is 0 comma 0. So 0 comma 0. Not always, but generally. Okay, so let's say this vector right over here is r vector. So this is vector r. So this is a position vector. So if you're taking so this position vector gives the position of a body relative to the arbitrary origin. So if there was something over here, let's take a man. So from the origin, he's over here. So it gives you the direction to where to look. So it just basically tells you where you must look from the origin to find the man, since you must look a certain distance right over here. So to represent this vector r, you will learn about why I'm representing it like this. later on, but right now you will actually represent this vector r by writing it as x. So it's moving x distance from here, I cap, which gives the direction from x-axis, plus y. So you're moving our distance of y from here, and j cap to give you a sense of direction. So y will mean the direction that you have, the length that you have to move from here to here, and x will be the length that you have to move from here to here, and I and j will just be the direction. So actually, this point right over here, where this man is actually x comma y. So this x and this y are the values that are written right over here. So this will be it for today's video. In the next video, we are going to talk about parallel transformations, and that we kind of discussed a little bit, very little bit. So in the next video, be prepared, I would say. Bye bye.